Perfect. Questions about anything? Doesn't look like it. Okay, I'll remind everybody where we ended last meeting. If I have a point P1, which is x1, y1, P2, x2, y2, all the way up to Pan, which is xn, yn, and I want to fit a line y, which is ax plus b. Let's see what you see in them. And I want to fit a line y, which is ax plus ab, and want to fit it in a way that it will fit the point as tightly as possible, hopefully going through all the points, if there is such a line. If there is some error in the point, then I want to minimize something, find the best line. And usually what we are trying to optimize is to do the following. Let's look at the point x1, y1. Let's look at the vertical arrow. How do I define the vertical arrow? What is a point which is vertically on the line, a point on the line, P1 prime? What would be the coordinates of this point? Point P1 prime, the point that is on the line L, on the line L, and vertically below P1. It will be, the coordinates of this point would be, since it's vertically below the x1, was no change, so it's x1. And what, if I put x1 inside this formula, it will, y1 will be ax1 plus b. That's the coordinate of this point. What is this distance, or at least the absolute value of this distance? This value is y1 minus the y1 prime, the values that I get from 1 y prime, minus ax1 minus b, minus this number over here, ax1 minus b. And this tells me what is the vertical arrow between the line and the point P1. Now, generally I don't want to mess up with this expression. I want to take this value, but P1 doesn't have any special rule. I have also P2, I have P3, I have all the way up to Pn, and each one of them will define its own arrow that the point introduced. So what I actually want to do is to take this expression, y, since not necessarily 1, but yi minus ax I minus b. This is what we said is a vertical distance. I'm trying not to hide to the camera. This is a vertical distance between the point pi, P1 for example, and the line, just the point on the line just above or below it. This expression can be positive or negative. I want to sum up these expressions, but I don't want one negative expression to cancel one positive. If the line is above one point and below another, I don't want to lose my microphone. I'm losing my microphone because it got broken something, so I'm improvising some fancy way to try to attach it. Okay, since I don't want these points to cancel each other, I'm summing up, but take it as square. that is, I'm summing up yi minus axi minus b. Take this value square and now sum it up for all the points. I goes from 1 till n, and what would be the line that we fit the best? We want to try to find a line. What do I mean as finding what's going to decide about? In order to find the line, I need to find A and B, because once I know A and B, I know what is this line. Find A and B that minimize over all choices of A and B this expression over here. It's not in the syllabus of the course, but that's the best fit line or minimum regression, or known as many different names, that all says here is a line that fits the best this set of points, when the error that I have in mind is sum up the square of distances between the line and each one of the points. Of course, if P1 happens to be on the line itself, then the error that introduces is 0. If all the points are on the line, then the best line that we can fit will give us error of 0. Usually it will not be the case. So what you see in this beautiful Java in geogabra applet is, in this case, I'm looking for all the points, say over here. I'm looking at all the points from A1 all the way to A15. Here we start to talk about material that is relevant to the course. We are looking at all the points from A1 to A14, and we're asking what is the best line that fits all of them. And it turns out that the best line that fits all of them will be the vertical line, just because the way that I put the point. If I'll be able to move the point, then this line will move or change its orientation accordingly. What is the error that we are considering? The error that we are considering is this green thing, square, plus this green segment, the length square, plus this one, for all the points. So that's the line that best fit this set of points. Let's ask what is the problem that we are trying to solve. In general, I'll show it with a mouse because GeoGabra does recall the line. The line is, I'm trying to find from now on, I'll just tell you that if I have a set of points, capital P is a set of points. P is P1, X1, Y1, that is P1, X2, Y2, all the way up to Xn, Yn. And very important, all these points are sorted from left to right. That is, X1 is smaller than X2 is smaller than ... Xn. So if I want to find the best line that fits this set of points, there are formulas that are known to the probably for many, many years that tells you the best A that you can find. There is a line that minimizes this error, the error that you see on the line, or the sum of green thing squares that you see on GeoGabra. And to find this line, you are using the following formula. A is just sum up the xi and yi minus sum up only the xi, sum up only the y, and multiply, yada, yada, yada. You don't need to memorize this formula. Just remember that it exists, and notice that we can compute it in linear time. Not surprising, why linear time? Because there is nothing here besides summing up different values. If I know what are all my set of points P, I know what is the error between the best fit line. From now on, my line will always be the best fit. What is the best fit between the line and the set of points? Questions so far? Cool. Next, we want to move into clustering of a set of points. See that it's a bit blurry in look, but I guess that's what our computer allows us. So at least I'll try at the moment to increase it a bit. So here is my set of points. Start at P1 and ends at Pn. I'll also do it on the whiteboard because it's a bit fuzzy. So here is my set of points. P is my set of points. It contains all the points from P1 up to P4. Remember, points are sorted from left to right. And then it continues from P5 up to P7. And if I wonder about, can I fit a line that fits all the points? Well, I can always fit a line that fits all the points. That's what you see on the geogabra right now. There is such a line. It will go somewhere like this probably, and will introduce a relatively large error because you see that there is no line that goes exactly through all the points here and at the same time through all the points here. On the other hand, if I'll ask you, if these points are sorted by time, these are the value of the y is the value of our stock of our company, and x is just the time. Now I'm asking, was there some period at which things were behaved linearly or behaved uniformly, and then there was some dramatic change, and from now on, everything has changed. Maybe we hired a new instructor. Maybe we hired a new. We changed something, and from now on, things has changed. The value of our company has changed. It kind of suggests that if you're looking for just two periods, and I don't know if the partitioning to two periods make more sense than saying everything else is the same period, but if two periods is the right answer, then it's not very hard to ask where should these two periods start and end. I will think that all the way the run of points or the cluster. I will use the word cluster or one together, and one of points is just a cluster of points. One of points is a cluster of points. And the reason that I want to sometimes call it one and not a cluster is that because if Pi and Pj are in the cluster, then Pi plus 1, Pi plus 2, Pj are also in the same cluster. That is, from now on, all my cluster will have the property that a cluster will start at some data point and ends at another data point, and all the points in between belongs to the same cluster. I cannot decide that P2 and P6 belongs to one cluster, while P4 and P1 belongs to another cluster. Cluster is a consecutive, contiguous set of points. Contiguous set of points. So what are the possible runs or cluster over here? I think that in this example it kind of explains itself. I'll probably say that I'll take all the points until P4 as one run, one cluster, and all the points from P5 until P7 as another cluster. How do I know that this is a good choice of clusters? because there is a line that fits very well all the points in the first one, in the first run, and there is a different line that fits very well all the points in the second run. How do I know now where should a run start and stop? Again, in the case of only two runs, I can check in linear time. In the geogabra, it goes quite fast. If I'll move, let's see if I remember how to use it. If I'll increase A, this example, to be 4, then I mean that all the points from A1 up to A4 should be in one cluster. A4 will be the last point of one cluster, and the points from A5 until the last point, A14, will be in the second cluster. In two clusters, I don't have path choice. But you notice what happened when I moved A. Right now I picked A as 4. Let's move A to be 5, meaning the first one must start at A1 and will end at A5 instead of A4. And the next one will, of course, start in the following point, must be A6, all the way up to A14. How do I know that this partition into two runs when A equals 4, is this better or worse than had I taken A to be 6 or A to be 7? Namely, take as one line all the points up to A4 and take all the points up to A4 and A5. I can have fewer points on the first cluster and more points on the second one. Let's assume that I take only the first 2 points to be on the first one. Is there a line that fits them well? Yeah, there is a line through 2 points. There is a line that goes exactly through them. You know, for every 3 points, there is a line that goes exactly through these 3 points, provided you draw them fat enough. And for these 2 points, there is a line that goes exactly through them. So I can ask, what is the error between this line and these points? And the answer will be 0. But you see as error 1, it is 0. What is the vertical error? The error that we discussed before. The error between the line and the points that fit it. Which line? Once you tell me what is a point in the run, I'll tell you what is a line. The line that best fit the point in this run, the line that best fits the point in this cluster. So I'm looking at the line that best fits the points in the first one, containing all the points from A1 till A2, and the best line that fits all the points to the next, all the following points must be in the same cluster because I limit myself only to 2 clusters. All the points from A2, the following of A2 will be A3, all the way till A4, must be in this cluster. I'll compute, geogabra does it for me, compute the best line that fits these points. And geogabra will also tell me that the error that I see for these points, error 2, that you see over here, the error 2, but the base, this sum of green segments, the length of these green segments, square and sum them, this error will be 307. That's error 2, the error with the second cluster. Error 1, the error for the best cluster. Well, there is a line that goes exactly through these 2 points, so the error 1 will be 0. And the total error that I'll pay will be what I paid for error 1 plus what I paid for error 2. How should I break these points into 2 clusters? Remember, cluster must be run. It cannot be that A14 and A1 will be in one cluster and A13 will be in another one. Once a run must be a consecutive set of points. Should I take A to be 2 or should I take A to be 3 or A to be 4? If I take A to be 4 instead of A to be 2, then the error from the first cluster is 2.7. The error from the second cluster is 220. When I sum these two numbers, it's about 223, which is better than the error that I had before when only A1 and A2 were in the first cluster. That is, for any value of A, I will have a different, I will have the first one ending at a different point, meaning the second one starts at a different point. And in each case, I'm looking at the error 1 plus error 2. And the error value will be error 1 plus error 2, which in this case is 239. What will be the best partition into two clusters? I'm just looking at all these values of error 1 plus error 2 and ask what is a minimum value. Right now it's 249. Right now it is a typo that I'll check later. Right now it's 241, 239, and when 222, 274, 309, and if I don't want to partition into two clusters at all, that is, the first cluster is empty, then I'm in 3170. So probably 220 was the best I could get. That if I only use two clusters. I had a way to get to 20, I think. No? If not, then 222. Yeah. That will be the best. Clustering with only two clusters. Okay. Now comes a really confusing part. How many clusters should I pick? Sometimes I know exactly what is the correct number of clusters, but you see that it's an emotional question, a logical question, much more than it is a mathematical question. I don't have the correct answer to what is exactly the correct number of clusters that I should pick. And if you know more about machine learning, you know about clustering algorithms in general, usually you expect the algorithm wants you to insert, to provide as an input the number of clusters that you want to obtain. You know, the algorithm says, for every number of clusters, I'll give you a different answer. In this algorithm, we will specify differently. We will say, maybe I want two clusters. Maybe I want less. Maybe I want more. I'll tell you in a second how. Maybe I want to actually create 3 clusters over here. I'm thinking my geogabra doesn't work well, but in this case, I have one cluster from A1 until A7, another cluster from A9 until A14, and another cluster that starts at A11 and end at A14. So I'll have 3 clusters, and each one introduce its different error. Now I have an error for the third cluster, which means what? Tell me what are the points in the third cluster, where does the run starts, where does it end. Find the best line, compute the error, do the same for the points in the second cluster, do the same in the point for the first cluster. For each one of them, find the best line and compute the error and sum up these errors. But here is the theological question. How many clusters will I pick? Should I go for as many as possible? Should I try to minimize the sum of errors that I'm obtaining from all the clusters? Well, if we'll try to minimize the errors that we are obtaining from all the clusters, the answer would be take n half many clusters. Right? N half many clusters will give you an error of 0, of course. When you sum up the error, and if you can use these many clusters, then I'll say through P1 and P2, there is one line that fits them with 0 error. Through P3 and P4, there is one line that fits them with 0 error, and so on. You're getting with a lot of errors, a lot of clusters, but for each cluster, each period, you find a line that represents this behavior in this period, in this cluster, in a perfect way. But that probably is not what exactly you want. If your data looks like in the slides, if your data looks like the data in the slides, here is a set of red points, here is a set of blue points, here is a set of purple points. When you are getting the input, you don't know what the color of each point. So you'll find probably a reasonable answer for this data is there is a linear behavior in a line that fits it quite well throughout all the points from P1 until P5. Maybe that's a good cluster. At P6, I'll start a new cluster all the way till P8, and then I'll start a new cluster. Why? Because each cluster is very close to the best line that fits it. So probably that is how I'll break it into clusters. Now we are getting to finally the formulation of this problem. Same thing that we had last class. I will say the user will tell me, instead of the user telling me the number of clusters, the user will tell me a penalty value, R. Some number R, which is how much, if a new point wants to be in a new cluster, this new point must pay for a new cluster. And R is a penalty for a new cluster. And so in this way, the user can say R will be huge, so probably I want only one cluster for all the data over here, or R is tiny, and then I'll have a lot of clusters, or R is in between. It's a parameter that the user can turn up and down and see what is the result for each value of R. Finally, what is the definition of the problem? Given all the points start at P1 and ends at Pn, finds n given R, well, another piece of input that the user specified. I want to know what are the points that are in the first cluster. These points start at P1 and will end at Pi sub 1. It's maybe a good idea to pull the PDF from the, if the font is too small, look at the PDF of the slides. Start at P1 and end at Pi1. What is your next point? If you just ended at Pi1, that is Pi1 is P5, your next point is undoubtedly, your next one start at P6. Your next one will start at Pi1, which was 5 plus 1, P6, and will end at some point. And so on. From Pi, it will end at Pi2. From Pi2 plus 1, the next point. If I2 is 8, then Pi2 plus 1 will be 9, all the way till P12. I'll have another cluster. What is the overall sum? What is the overall errors that I introduce? I'll take the first run of points from P1 up to Pi1. I'll find the line that fits best these points. I'll find the line that best fits these points. I'll compute the error, the sum of the vertical error, with respect to these points and with respect to this line. This is one error that I'm paying, plus the error that I'm paying from the best line that fits the next one to this line, plus the error that I'm fitting to the last cluster to the best line that fits these points. However, for each cluster, I'm also paying this penalty R, whatever the user gave it. R is $5, meaning every new cluster I have to pay $5 more. R is 0, probably you'll get a lot of clusters. R is infinity, probably you'll get only one cluster. And now the question is, how should I break my points into runs, into cluster, in a way that minimize this creature? So I want to minimize this creature. How many ways, given endpoints, how many ways can I break them into runs? It's a cute combinatorial question. If you want to say I have k runs, then essentially you need to pick where between the points you are placing, like, breakpoints. If I have all the points from P1 to P7, I need to ask between these three, which points do I pick a breakpoint that will introduce a new clusters. If you have k runs, then you have k minus 1 breakpoints. You need to pick where to put them. So it's roughly n choose k, roughly n choose k. K is the number of clusters, which is, what's important about it, which is exponential. It's roughly n order of n to the k. It's a lot. I cannot consider always to break into its exponential algorithm in the number of clusters, which is not surprising because most clustering algorithms have exponential running time in the worst case. All clustering algorithms also have pretty good heuristics that usually leads to very good results, much faster than exponential, but the worst case is exponential for most of them. So the reason that I'm spending so much time on this problem is that dynamic programming is, in a very surprising, very ingenious, which it was mine, very ingenious way, suggests a very fast algorithm and square time algorithm to find the optimal clustering. So here is my algorithm. In the preprocessing stage, I'll say that for every pair of points pi and j, as long as j is smaller than I want to compute the line Lij. What is this line? This is a line that best fit the point, give me the minimum error for the point start at pj all the way up to pi. That is, I don't know if the run from j to I, if this run of points will be in the optimal clustering, but if it is, then in the pre-processing stage, I want to know what is the line that best fit these points. And I also want to know what is the error that it will introduce. How well does this line fit this point, and what is the error that it introduces? Int error, the sum of squares of the vertical distance. The same algorithms that we saw 2 slides ago. This algorithm that we compute this formula, and this formula gives us the exact error. We will do it in the optimal clustering, but for every run. How many runs do we need to consider? Only n squared, right? There are only n squared many runs, because once I told you what is I, and once I, well, can you see me? Once I told you where is I, once I told you where is j, then the run is uniquely determined. You know what are the points from, if I told you my run will be, or I think about the runs that start at P5 to P7, you will say, here is the line that best fit these points. And I'll do it for every value of I and j in the pre-processing stage. I still didn't start the real algorithm. So I'll compute, I have these values, and the error for each one of them. And now, like in all dynamic programming algorithms, we have a table. I mean, I need to store a table of values. For Dijkstra, it was the estimated distance to every vertex. For LCS, it was as a stable contained as estimated the length of the LCS for sample fx of x and sample fx and y. Here, I'll define Ci to be, let's follow it directly, is a cost in what terms? The cost in the term of the formula that you saw one slide ago. This fancy long formula with a lot of terms. I'll assume that Ci will contain the cost of the optimum clustering of all the points, assuming that my data starts at P1 as before and ends at Pi. The Ci assumes that the last point that I know about is Pi. And we'll find the best clustering, the best partition into ones of all these points. It doesn't mean that C1 assumes that there is necessarily only one clustering. Maybe there is one, going back one slide, maybe there is one cluster, maybe two cluster, maybe three cluster, whatever. But on any rate, Pi is the last point that I'm going to care about when I'll define Ci. No more points after Ci. That is, this term just includes both the sum of errors of and the sum of errors of the lines to the points, the vertical distance, you don't see it, the vertical distances of the points to the line. And it contains also the sum of penalties, because when I sum them all together in this formula, we saw that maybe less cluster, maybe more clusters makes more or less sense. No matter what it is, I wanted to compute what is Ci. The best way to partition the points from P1 up to Pi. Just for the warm-up, here is P1, here is P2, and I'm asking what is C1. C1 is the best clustering of the set of points that starts at P1 and ends at P2. What should I write in C1? Or what should I write? I'm sorry, C2 is the optimal clustering of the ones that start at P1 and ends at P2. What is C2? Be careful with your answer. What is C2? Remind you again, it's the best way to cluster the points. In C2, I'll assume that I broke all the points from in the ones that start at A1 and end at A2, the ones that start at A1 and ends at A2. Start at A1 and ends at A2. They're both in one cluster. But what do I pay at this point? What should C2 contain? Going back one slide. Oh, on this slide, you see that the error will be how well can I fit a line to the set of points that start at P1 and end at P2, plus every run pays a penalty. Every run pays a penalty, like the rightmost point of the run will pay a penalty. So C2 will not be 0, will be R. Because no matter what, I have to pay one penalty for C2. C0 in this case. I don't have any penalties, it's just 0. Now, what happens when I goes from 2 all the way to n? What is CI? And here is, you see, a known property of dynamic programming. I spoke about this algorithm, I introduced it for over an hour, but the code is going to be so simple. So let's look at the code. For I equals 2, what is CI? CI says the point PI must be in a cluster. I'm adding the point P3, and I assume that P3 must be in a cluster of itself. It opens a cluster, and you note, no matter what is this cluster, a point that opens a cluster, the rightmost point in the run has to pay R dollars. So P3 has to pay $1. So CI is going to pay R dollars no matter what, and it will, but now I'll ask if P3 is in a run, who is else in a run with P3? What is the leftmost point of the run that contains P3? Again, what is the leftmost point of the run that contains P3? I don't know if the leftmost point will be P2 or it will be P1. Or in general, if I have already the point, if I already found some fitting of the points P1, P, P2, P3, P4, P5, P6, P7, and I'm just adding P7. So I equals 7. I'll assume that P7 being the white must be in a run. Oh yeah, sorry, yeah, thanks. P7 must be in a run of itself. Being the rightmost point of a run, P7 must be in must pay R dollars. So we are paying R dollars because P7 will say I'm the rightmost point of some new cluster. And now J asks what is the leftmost point of this cluster. What is the leftmost point of this cluster? What is the rightmost? What is the rightmost point? Correction. What is the rightmost point? The rightmost point of the previous cluster. So if I'm adding P7, what could J be? J could say I can be 6, I can be 5, I can be 4, I can be 3, I can be 2, I can be 1, I can be 0. For example, if J equals 3, then P7, P6, P5, and P5 and P4 will be in one cluster, and somehow I had to optimally cluster all the points that came from J, Pj, all the way to the left. And again, I don't know what is J, but what will be my cost altogether? Some oracle came and told me what is J. What is the overall cost that I need to pay? I need to pay R. You don't see it. I need to pay R for the new points. I need to pay the error of the run that contains pi, and what is the length, what is the error, sum of vertical error that pi introduced. It is pre-processed beforehand. That's the error that I computed earlier, which stands for e from j plus 1 all the way to I. That's the best error, the best line that I can fit to the point from j plus 1. J plus 1 is a point, is the first point of the new cluster. I is the last point of the new cluster. That's the sum of errors of the vertical error of the rightmost, this new generated cluster. R plus this one is what I paid for the new cluster. How much do I need to pay for the previous clusters? Everything from J to everything from J, including J, all the way to the left. How much should I pay for the clustering of everything to the left, penalties plus errors? Well, it's a hard problem in general. However, luckily, I already computed it. That was for smaller I. That was when I was smaller, when I used to be J some time ago. So what I need to pay is everything up to the jth point, which is stored at Cj, plus what I'm paying for the new cluster, which is R, plus the sum of errors, of the vertical errors between the best line and the points from the j plus 1 all the way to I. J plus 1 to I are everything in the new cluster. Which value of j should I pick? The one that gives me the best back for the money, the one that minimizes this error for this choice of j. It's as simple as it. So Ci is nothing but the minimum of this expression when I check all possible j's. And now I know what is Ci, so I can move to Ci plus 1. In addition, Ci also remembers in the way that the pi value. In summary, Cj need to ask for what is the PC7. C7 will say, oh, if that's the best clustering that you can get, then please remember that the rightmost point of the previous cluster was P3. So P7 will remember that the rightmost point of the previous cluster ends at P3, if that's indeed the minimum clustering. So once again, see that this, in the case of two clusters, that's exactly what this geogabra gives us. And so on. So if these errors, E of j to I, if these errors are already computed, which you can do trivially in n cube, you can do it a bit better in n square, but n cube will be just fine, then this algorithm is really fast. For every I, just check all the previous values of the j's that came earlier, which takes only I time. So all in all, this whole algorithm runs in n squared time. N squared time is no extra work. The n cube will be extremely trivial. N squared will be a bit faster. The only part that took the n squared was to compute these values, the E from j to I. If you are doing it naively for every j and I, you are computing this error. It will take linear time for every j and I, but you can do it in n squared if you are a bit clever. Anyhow, everything here in the memorization just take advantage of the fact that when I am about to compute Ci, then for every j that is smaller than I, for every j that is smaller than I, Cj minus 1 is already computed. Well, Cj is already computed, waiting for me in the memory, just the cost. That is, when I'll back to my geogabra, when, in this case, for example, I'm adding A6. A6 will be the first point of a new cluster, maybe, and A6 needs to know what is the total error that I did for the previous cluster if I want to say A6 will be in a cluster of itself. Why would it want to be in a cluster of itself? Because maybe as a cluster of itself, maybe A6 is so far away from all the points in the previous cluster, A6 is really very, very small or very large, so it wants to be, it was for me to pay the penalty for A6 to be in a cluster of itself. Or possibly A6 will be in the same cluster as all the points preceding it. So what will the value of J be in this case? A6, the optimal clustering for A6, including all the points previous to it. So I'll check the case of J equals 0, at which C of J initialized to 0, and all I pay is the cost of one cluster, R. Again, I'm just solving the case of I equals 6, and if for I equals 6, the best that I can do is one cluster, it means that I'll get to J equals 0, C of J is 0, and the total penalty that I'm paying is R for creating one cluster, 1 times R, plus the error of all the vertical segments, the sum of squares of length of all the vertical segments that fits all the points over here. What happens when I equals to 14, say? I equals to 14. And I'll assume that if two clusters are the same, then what will be the value of J that I'm going to check? I equal to 14, and I'll check all the value of J. I is 14, I'm taking all the value of J, where the J start from 0, which you see right here. J start from 0, then I'm only paying for C 0 plus 1R plus E of everything from J plus 1, A1 all the way to A14, that is the error that I'm paying over here, written, given as error 1, over a, or given as a typo, it should be a error 1, because it is not the first cluster. Yeah, it's all the error here is that the second cluster, the first cluster in my Java is contains only the point 0, and I'm paying 0 for the first cluster, the error of 300 for this cluster. Or possibly I'll check J equal 1, paying 1R for the first cluster plus error 2 for the second cluster, so paying 2 times R plus the sum of vertical guys, which is written as error 2. J equals 3, J equals 2 right now. That is, the last point of the previous cluster is A2. J equals 3, J equals 4, J equals 5, J equals 6, and at each value, my algorithm will ask what is the total sum of errors for these guys, plus what is the optimal clustering of everything that happens before. However, I don't need, and that's the ingenuity of the dynamic programming, I don't need to solve the problem of the optimal clustering of the previous points recursively. That's how I avoid the exponential running time. The cost of this clustering is already computed. Why? We are again recycling the idea that optimal solution of smaller problems are used in the optimal solution in larger problems. It is, I don't know that the previous cluster ends at A6, but if they do end, if all the previous clusters, when I'm adding A14, I'm not sure that A7 is indeed the first point of the cluster with A14, but if A7 is indeed the leftmost point of the cluster of A14, it means that A6 is the last point of the previous cluster. And in this case, how should I cluster all the points from A1 to A6? I'll use the optimal clustering and pay a penalty, which is as small as possible. I hope this idea will sink. I'll give a few more examples, and I'll refer to videos that I explain it again. I'm not sure that today I did the best way. We are done with dynamic programming. We are done, I think, with complicated topics of this course. Let's move to twice. Twice are fun. Everybody understand twice. Think that it's more friendly. If there are no discussions. We'll talk about twice. We'll talk about twice, and then we'll see that and from twice we will move to
Unzoom the slides on the.
Yeah, I'm putting it. Yeah, I see that there is an issue. Okay, our plans are to talk about twice. It's not a spelling mistake. Let's the correct spelling. It's one of the best branding of the data structures, I think. Finding a good catchy name. And after twice, we will talk about suffix trees, and then we'll talk about quad trees, where we'll realize that quad trees are actually just one type of twice. And probably union find and call this course a day. So, what is a twice spell in this case? So, I need a data structure for a set of words. Set of words like words in the alphabet. Maybe I want a data structure to keep a dictionary. Or maybe these words are proteins, maybe, and or DNA, and my alphabet just contains the 4 bases of DNA, or any type of alphabet at all. And I want a data structure that will allow me to insert a new word into my dictionary. Word, just a string, insert a new word, discover the new protein, somebody decided that a new word is a word in the English dictionary, a new student came and you are putting her or his name in your storage. So I want to perform an insert into S. S is my dictionary, the set of students, the set of words that are already in my data structure. The student might have left the university, so I want to delete the student. Or I want to ask I'm playing Scramble, and I want to ask if a hello spelled in this way is hello is a word in S or not. If it's a student or if it's a protein, maybe I want the data relevant to the student as well. It always comes with some auxiliary data. So when I do find, I don't only want to know exists or doesn't exist, but also to know all the auxiliary data. Where the student is living, what the grades, and so on. Now, these three operations, I can use hash table to solve the three operations, and actually hash table is likely to perform faster than try, but asymptotically it still will be the same. I'll explain why. How much time will it take me to perform any one of these operations? Well, if the name is very short, if the name is only contains 3 letters, presumably it should take a constant. But what if I want strings or words that are becoming longer and longer? Text or patterns that are becoming longer and longer. What is the best that I can hope for? Let's assume that K is a number of letters in this word W. That is, just to read the word W, just to know what is this word, I need to spend at least K time, at least K checks of each letter, what is it. What's the best I can hope for all these three operations? I hope to perform them in times at least order K, but usually in most, if I'm using a search tree, usually I'll have to pay O of W. Over here, the length of W, that is K, how many letters it is, plus usually in search tree, there is some log n involved that are, depending on the n will be the number of words in the dictionary. Now, hash function, of course, if you're using hashing plus dot product, of course, I need to still pay the order K just to read all the letters, but I hope that after that insert or delete takes order 1, but that's on some average sets, best case, but it's randomized. Try will be able to provide all these operations in order K. Notice, doesn't care at all how many other words, how many other students there are. I'm paying just the optimal time, just as the number of letters in W, that's the running time of my data structure, and mostly it will help me perform many other operations. Mostly, and that will be probably the nicest application out of it, is that let's say that you are going to Google and you type www.cs.arizona something. You typed it once and will access the department web page, and then you are if you have autocomplete on, you type www.c and suddenly the cs.arizona your browser will guess that that's a last, that might be the completion of the word that you just typed. How does it know to access out of all the addresses that you ever access? How does it know that that's the most likely one and to suggest only this one or only 3 options? And this will be one of them. That's another beautiful application of what we will see. So it will know that this is a auto completion, but if next you'll see www.cs. And then you'll type the S and you'll type D, it maybe will be jumped to try to complete to Duke and not to Arizona. How will it know what is a reasonable completion of the world is part of what we are going to see. Another application similar to it is incremental search in an editor, but nobody got to say. What is incremental search? You are looking for your document and you type double and you're typing search, but you are saying, I want to type incremental search, and you type W, and in the big document, your cursor jumps to the first appearance of W. You're typing this another W, and now your cursor jumps to the first appearance of WW. Add another W, add CS, and each time your cursor jumps to where, what does it jump to? To a word whose prefix is exactly what you typed. And we'll see how we can do all of it without storing all the prefixes of every possible word all at the same time. Okay, but at the moment we will be more humble. Our attempt is just to provide a data structure that can perform insert of a word, delete of a word, or find a word, each one in an optimal time of the letters in this word. And here is the structure of a try. If you are using C, you will define a structure of a node, and this node, let's assume that my alphabet contains 4 letters, namely A, B, C, and D. Normal tree binary trees will store in each node a key. It will store a left pointer to the left node, and a pointer and the right pointer to the right node. And in this way, I'll build a tree. Twice similar, but not identical. Again, I assume an alphabet of only 4 letters. If I have more letters, then the nodes are larger. And that's, by the way, one of the disadvantages of tries, that each node might be chunky, big, larger. So here is one such word, and this word consists of an array of, my alphabet has 4 letters, so it will be 4 cells. If I had 22 letters, then I had 22 cells, plus another cell that contains a flag. Flag that will be yes or no. So in C, I'll define an array of 4 letters, each of pointer to another node of the same type, node of R, plus the flag that we'll see its rule in a moment. Right now, I'll tell you already what is its rule, but it will not make sense by far. At this moment, the rule will be that each node will correspond to a word, W. Each node in the tree that I'm going to build will correspond to word W, but W might or might not be necessarily in S, in the dictionary. If the word that it corresponds to is in S, then the flag will be true. If the word that this node corresponds to is not in S, then this flag will be false, 0. Doesn't make much sense now, but it will make sense in a second when we'll see an example. One example will make everything clear. And trust me on it, I taught thousands and thousands of students about tries, and they all understand. Try, just what is this brilliant branding, is the combination of tree plus retrieval. No, plus retrieve. That's the breaking. So I want to build a try for the set of words A. A is a word, contains only one letter A. Another word is a letter B, and another word is the string DBB. So 3 words in S at the moment. Okay, that's the try that I'm trying to build at the moment. That will contain these 3 words. At the moment, I really don't care about where I store the auxiliary data, because every word corresponds to a student, there is some detail with the student. Doesn't matter. I just want data structures that will tell me right now if a word is in S or not in S. So here is how the try looks like. Every node, as we said, is an array from the type that we saw in the previous slide. An array that consists of 4 cells. The first cell corresponds to the letter A. It doesn't mean that I store A in this cell. I do not store the A in this cell. What I do store, you see it on partially see me. So you see a little a above this cell. It does not mean that that's what the cell stores. It does not store the letter A. Instead, we think about the cell as it corresponds to the letter A. What do I store in this cell is a pointer, the address in memory, an arrow, if you wish, to a children to a different node. And as we said, every node corresponds to a word right here. And I'll tell you in a second how do I connect a word with the cell. So there is an arrow that leaves this cell. An arrow that leaves a cell that corresponds to it. Now, this arrow is nothing but an address in the memory where this node, this child, this node, is stored, like the left child and the right child. Where are they stored in memory? But as an intellectual trick to understand what the try represents, I'll think about the arrow that leaves the cell of A. I'll think about a label to the arrow. And this label will be the letter that it left from. So the arrow that comes from the cell of A, I'll think about this arrow as having labeled A. The cell that comes from B has the label B. Cell that comes from C, well, C is empty, but if I had an arrow, it would be C. Arrow that comes from the cell of D, I think as it has the label D. And again, what determines what is this label is where the arrow is coming from. It always, when I'm having the arrow or the address in the memory, it's always the address of the first part of the array in the memory. It's irrelevant which part of the array that I'm pointing to. Don't look at the destination of the arrow. The arrow comes from B, so put a label of B when you try to understand what the try stores. Again, label of an edge is where this edge is coming from, the letter of the edge that it comes from. Okay, so I have a cell that comes from D. I have another arrow that comes from the cell B, another one that comes from the cell of B. So this edge is labeled D because it comes from D, comes from B, comes from B. Cells that I didn't write value in general, specifically think about it as containing null, containing address of null. Now, I told you already that every node corresponds to a word, but this word is not necessarily in the dictionary. It's not necessarily a student currently at the university. How do I know what is a word that a node corresponds to? Answer, to know what is a node corresponds to, concatenate the labels of all the edges, concatenate the labels of all the edges in the path to the node. Concatenate, put one after the other, the labels of all the edges to this node. that is, what is this node corresponds to? Let's concatenate the path to it. It consists of A, and that's it. So this node corresponds to the word A. What does this node correspond to? It corresponds to the word B. What does this node correspond to? Let's concatenate the edges on the path to it. It's very confusing, not the children that comes from this node, irrelevant. Not the labels on the vertices themselves. Concatenate the labels that you are mentally putting on the edges. And to know what's the label of the edge, you know where the edge is coming from. This edge is coming from the cell of D, so you label it D. This edge coming from the cell of B, so label it B. And this node corresponds to the word AB. Make sense? This corresponds to, sorry, this node corresponds to the word DB. What about this node? It comes to the path to it, and it's a tree, so there is a unique path. The path to it is labeled D followed by B followed by B, so this cell corresponds to the word DBB. This node corresponds to the word DB. This one corresponds only to the word D. And now we can understand what these flags all try to say. I'm asking, do I have to have this node in the try? Yes, because it's on the path to a word that is in the try. I cannot eliminate this node. However, I'm asking, this node, like every other node in the try, corresponds to some word. What is this word? DB. Is DB in the dictionary? No, DB is not in the dictionary. So the flag of this node is 0. That's because DB is not in the dictionary. What about this node? This node corresponds to the word D, not in the dictionary as well. The dictionary contained only the words A, B, and DBB, 3 words. So the flag of this node is 0. The flag of this node is 0. The flag of this node is 1, of course, because DBB is a word in the dictionary. And if you think about it, every leaf on this tree, every leaf of this tree will have a flag of 1. You'll understand why in a second. Make sense? So how will I know if the word DBB is in the dictionary or not? I'll go to the root. I'll say, oh, it's the word DBB. The first letter of DBB is D, so I'll try to follow the cell of the pointer of the cell of D. I'll continue following by the cell of B. What do I mean by try to follow? It might be that I'll do a search for DB. I'll do a search for DBD, DBD, D like dog, DBD, trying to leave from this D, but this D points to null, points to nobody, so I'll assume that DBB, D as a DBD, dog, Bob, dog, is not in the dictionary, so my search will end. On the other hand, as long as I can follow node with the words, I'll keep doing it. Let's see the code of the search algorithm. P, I'll start my search at the root. I assume convenient of C, I'll write it in C. In C, the last character of the string, you reach the last character of the string if this character contains 0. Every string has 0 at the end. Might be. So what are we saying? I will start in 0, and I'm going to check each lecture at a time. So if W of I is null, it means I'm at the end, I'm visiting P will point to one of the nodes. If this node that P is pointing to has a, if I reach this, node. Maybe it's a world of S, maybe not. In this case, I'm returning the flag of this node that I just visited. Maybe it's true, maybe it's false. Otherwise, if P dot A of Wi minus A just tells me if it's A, then it will be cell 0. If it's B, then cell 1, cell 2, cell 3. If P at this condition points to null, you cannot continue. That was a case of looking for DBD, dog, Bob, dog. I was running into null, and in this case, I'll return, no, the word that you're after is not in W. Otherwise, this address is not null. Go to this address. P will go to point into this new P. Let's see in a quick example. I'm going back one step. So I'm doing a search of a DB, the word DB. Start from I equals 0 and P equals the root, as before. I'll just copy from the tree the part that I need. So this part, here is the root. The last element, the one that points to D, points to somebody else. So I'm saying follow this root, go to this new node. So now P points to this guy. What is the word that is associated with this guy? This word corresponds to D. And I in this case is in this case 1. Now, what is the string at index 1? It's a B. So follow the node from B. Follow the node that leaves the cell of B. And you got to this word. What is a word that this cell corresponds? Notice that the cell doesn't need to store this word. But the cell, think about it as it corresponds to the word D. To the word DB. The root, I followed this D, I followed this B. I increment I, in this case I equal 2, meaning that I see the \0 at the end of the string. I get to the end of the string. So what do I return when I visited this node? I got to the end of the string. So I'm just returning the flag of this node that I'm looking at. I'm looking at this node that corresponds to DB, but the flag of it, the flag is 0, meaning it corresponds to a word, but this word is not in my dictionary. It's not a student at the university, so I'll return false. In this case, I just return the flag. What would have happened in the same tree? What happened in the same tree if I'm looking for search for the BBA? I start when this is P points to the root. Looking at the string at index 0, it's a D. So P will point to this guy. This is not a null, so P will point to this guy. Next letter is B. The B cell points to an existing node. Follow this new, follow P. So P now points to this node. The next letter is again B. points to this guy. And the last letter is A, so I'm trying to follow the A over here to a node that it points to, but I'm running into null. I run into null, so I realize that the answer of my search is no. So my search in this case will run into this case, this node is null, so return false. And that's immediately also suggests how to insert and delete nodes from the tree. You understand exactly now, going back to the tree, if I want to insert the word DBBA, you understand how to do it. You will try to first find the word DBBA. You run into this node that has a null point from the A over here, and you'll realize that you have to add one more node right here. No attempts to balance or rotate or move parts of the try. The try is completely determined. There is no rotation, no balancing involved. Okay. And the insert algorithm will be completely trivial, and the delete algorithm will be completely trivial. What do I do when I delete a node? If I want to delete DBB, I first find it. I cannot delete it unless I find it. I'll find it. It has a flag of 1 if it's in the dictionary. I'll replace the 1 by 0. And now I realize that, hey, do I really need this node? Its flag is 0. All its children are null. It doesn't have any children. It's a leaf. So I don't need this guy. So let's delete it and go to its parent. At this point, I'll ask the same question for its parent. Do I need the parent? Maybe not, so I can delete its parent, its parent, and its parent. So there is a whole cascading effect. And everything in order W, and everything is very, very efficient. Thanks, everybody. Bye. Tomorrow we'll do some, we'll play a bit more with the LCS and edit distance and the Frachet, solve a few questions together, our last active learning. Thanks, bye.